Good morning, everyone. Welcome to another meeting of our series of talks about active BE stars. So our talker today is Kareem. So Kareem is a postdoc at the Harvard Institute for Theory and Computation, and he recently completed his PhD at Berkeley. He also has an appointment at MPIA at Heidelberg for 3 months each summer. He has broad research interests including binary evolution, galactic stellar populations, and stellar feedbacks in galaxy formation. And his most recent work has used a mix of binary evolution calculations, large-scale surveys, and targeted observations of individual objects to study binaries. So you can take it away, Kareem.
All right, thanks for the introduction. Thanks everyone for coming. I just want to say as I'm starting that I want to use the time in a way most useful for everyone. So if you have a question while I'm talking, feel free to ask while we go. I realized I was putting together the talk, I have a lot of slides, but I won't be upset if I don't get through everything and we discuss your questions instead. So today I'm going to tell you a story, essentially, about how binarity can complicate stellar evolution calculations, but also enrich them and make them more interesting. And the story starts really as long ago as you can imagine people looking up at the night sky. They looked up at the night sky and they realized that the stars were not completely static, but some of them changed. And the one that changed the most obviously was this one, Algol, which every now and then would suddenly get fainter. Then be bright, and then it get fainter again. And this was confusing and inconvenient for ancient astronomers and philosophers who thought that the heavens were basically static, perfect, and unchanging. And in fact, in Arabic, Algol means demon. And throughout a lot of antiquity, the star was associated with bad luck. In fact, more than 3,000 years ago already, the ancient Egyptians published a so-called calendar of lucky and unlucky days, which you can see shown here. And the calendar divided the year into about 1,000 segments, so each one about a third of a day, each one either lucky or unlucky. And if you just take a periodogram of this calendar, basically a Fourier transform to see what frequencies are most common in it, you see two periods. There's one, which is 29.6 days. That's the period of the moon. But the second, 2.85 days, is the period of Algol, of it is brightening and fainting and getting fainter. And we now know that the reason Algol periodically gets fainter is that it's an eclipsing binary. And it's not clear whether anyone in antiquity understood this, but as far as I know, the first light curve that really shows how it gets fainter wasn't published until a little over 100 years ago in 1910 by astronomer Joel Stebbins. You can see it here. And what's plotted here is how bright the star is as a function of time over about 3 days. You can see there's one dramatic dip where it gets almost a factor of 3 fainter every 3 days, and then one less dramatic dip. And we now know this is a primary and a secondary eclipse. And so these kind of eclipsing binary stars are the best places to measure stellar masses and stellar radii. Those measurements depend basically only on well understood physics, to first order at least, gravity and geometry. And so already by about 1930, the parameters of the stars in Algol were pretty well known. There's a main sequence star that's about 3.5 solar masses, and then a subgiant star that's about 0.8 solar masses. And you probably know, but when I say main sequence, I mean the star is basically in its adulthood, whereas a subgiant means the star has already evolved off the main sequence. It's farther along in its evolution. And it was pretty quickly realized that this doesn't seem to make sense. This is called the Algol paradox. And when I say it doesn't make sense, what I mean is we know that, or we think we know that the two stars in a binary formed at the same time. So they should have the same total age. And we also think we know that more massive stars from stellar evolution calculations have shorter lifetimes than less massive stars. So how is it that in Algol, we have a much less massive star that has progressed farther in its evolution than a more massive star. And that's the algal paradox. The answer to the paradox is already suggested in this artist's illustration here, and that's that algal is a binary with interaction between the two stars. In particular, there's ongoing and past mass transfer from the lower mass star to the higher mass one. And we think that initially the subgiant star was actually the more massive star, but in the meantime, it's donated a lot of its mass to the companion, in the process making the companion more massive and spinning it up. And this just makes possible a much wider diversity of evolutionary scenarios than you can have with single stars alone. And so the theme to take away from algal, which will come up again in the talk, is that binary evolution essentially makes things more interesting, such that the rules of single star evolution don't apply, or at least apply with caveats. Okay, now for another puzzle, which I'm sure most of you know of, given that this is a technical audience, but I wanted to just start with a simple introduction. So it's been known for more than 100 years now that, well, I should say, first of all, most stars, when you take their spectra, have spectra dominated by absorption lines. But it's been known for over 100 years now that some stars show these prominent emission lines, especially in the Balmer series, but also in other lines. And the spectral type where this phenomenon is most common is B stars. So that means an effective temperature of about 10 to 30,000 Kelvin, and something like 1 in 10 to 1 in 20, depending on spectral type, B stars show these kind of emission lines. You know, some have moderately strong lines like this, where they're obvious in H alpha, but not in other lines. In some cases, the emission really dominates over everything. And then in some cases, you barely see the emission lines, just a little bit of infilling inside the strongest lines. And if you compare the spectrum of a BE star to a normal B star with the same temperature, you see two main differences. So one is the presence of emission lines, which I already said. The other is that there are many narrow metal lines found in normal B stars that seem to be missing or smeared out in BE stars. And the reason for this is now well understood. It's that BE stars are rotating rapidly. So if I take this stellar template of a normal B star and I just spin it up, you know, I spin the star and rotationally broaden it, then all the narrow lines get smeared out and you're left with these broad lines found in BE stars. So the explanation for the BE star phenomenology, which is pretty broadly accepted over the last 100 years or so, at least in you know, for most BE stars, is that BE stars are rapidly rotating. So they're rotating close to their critical velocity, which means several hundred kilometers a second for typical main sequence stars. And they periodically lose mass through these equatorial decretion disks. And that's where the emission lines are coming from. So I suspect most of you know everything I said so far. Something I didn't know until recently is that in the Pleiades, one of the more recognizable things in the sky that even I can find, 4 of the naked eye stars are BE stars. And this is one of the more extreme cases, but the point is BE stars among massive stars are extremely common. So whatever is responsible for them plays an important role in the evolution of massive stars in general. So just to emphasize that the rotation velocities of BE stars are different from those of normal stars of the same spectral type, here's a compilation of rotation velocities for BE stars from the literature. You can see there's a little bit of overlap where there are some rapidly rotating stars that don't have emission lines, but there are really no rapidly rotating there are no BE stars that are not rotating at least half of their critical velocity, or at least very few. So there's general agreement that BE stars are rapidly rotating, but what there hasn't been agreement about, at least you know, not for a long time, is why they're rotating so fast in the first place. And of course, as always, there are many different hypotheses. One is that maybe BE stars are just born rotating rapidly from high angular momentum gas clouds. Or maybe they're born rotating, moderately rapidly, but not close to breakup. But then over the course of their evolution, meridional currents can spin up the outer envelope by advecting angular momentum from the inside of the star to the outside. And then a final possibility is that BE stars are spun up by mass transfer from a binary companion. And so you can probably guess from my title and what I've been talking about so far that I'm a fan of this binary interaction scenario. But what I'll emphasize early on is, probably there's more than one channel to make BE stars. So there's not any reason why one of these has to completely dominate. But most of my talk will focus on this channel. So I just want to say a little bit about how I got interested in this problem in the first place. I didn't know anything about BE stars until a couple of years ago, but in my PhD research, I spent a lot of time looking for black holes in binary systems. And so a couple of years ago, within a few months of each other, there were these two really interesting binaries that are black hole candidates were announced, are called LB1 and HR6819. Both of them contain BE stars and were at least proposed to contain stellar mass black holes. And so because I was working on black holes, I started working on these systems. And so the observational data for both of these were pretty similar. I'll just show some examples. So here's a cutout of the spectrum of the first one, HR6819. And I'm just showing spectra taken on 2 different nights. And the main thing to take away is there's this large emission line, which doesn't seem to move in velocity from one night to the next, at least not very much. And then there are absorption lines, which do move a lot in velocity from one night to the next. And so that suggests there's a component that's RV variable, a binary in absorption, but the emission lines don't seem to be RV variable, at least not very much. And so the argument for a black hole in these systems went something like this. We see a component in absorption that's orbiting something, and we don't see the thing that it's orbiting. So we don't see a component moving in antiphase. And just from the kinematics of the orbit, you can calculate what the mass of the companion must be, given an assumption for the mass of the B star, the B star being the thing making these absorption lines. And it seems if you, from the spectral type of the absorption line star, which is about B3, if you interpret it as a main sequence star, it must be about 5 solar masses. And you can then infer that the companion must be also about 5 solar masses. But we don't see a companion that looks like it's about 5 solar masses moving in antiphase. And so the companion could be a black hole. And so in this scenario, we haven't yet explained why there's a BE star in the spectrum. And so the one possible proposal is that it's a triple, where you have a B star, this is the absorption line component, in a relatively compact orbit. These are periods of order a month or a couple of months, orbiting an unseen companion. And then the BE star would be off in the distance, at something like an AU to tens of AU, where its nature as a BE star is not related to the inner binary, most likely. My conclusion will be that this isn't the right way to think of these systems, but that actually there are only 2 components in them: a BE star, which is being orbited by a B star. But in order for this picture to work, the B star can't be a normal main sequence star. It needs to be much less massive than suggested by its spectral type. And it's this large mass ratio difference that will make it look like the BE star is not orbiting at all, or is only a little bit RV variable. And so I'll just briefly explain how I and others came to that conclusion. So I used a technique called spectral disentangling, which is illustrated in a little movie here made with real data. The basic idea is, you have many different spectra of a binary taken at different phases. And you start with the ansatz that the spectra are the consequence of 2 spectra that are shifting back and forth, that have some velocities. And let's play it again. And that the shape of the spectra doesn't change over the course of the orbit. The only thing that changes is the relative velocity. And under that ansatz, it's just a linear algebra problem to solve for both the velocities and the component spectra. And so what's illustrated here is the composite spectrum you get for a small portion of the spectrum in HR 6819 when you shift back and forth the inferred spectra of the two components. And here I'm just showing for the same system some different portions of the spectral line. And you can see in all of these, the black line is the data, the red and blue are the two components that are not directly observed, but are inferred. And then the cyan line, which sits on top of the black line, is their sum when you add them together, which generally reproduces the data. And so here you can show the full reconstructed spectra of the two components. So there's one component that is hot and has narrow lines. And there's another component, which is a BE star. I'm not showing H alpha here, but you can already see emission in some of the higher order Balmer lines, which has only these broad, rotationally broadened lines, and also emission in some other lines. So you also get RVs out of this analysis. Essentially, they're the velocities for which your two components can best reproduce all of the observed composite spectra. And the main thing to take away is that although the BE star is not moving very much in velocity, it's almost imperceptible compared to this narrow line star, it is moving in antiphase with the B star. And just from the just from these velocities, that suggests the two stars are orbiting each other. So these two stars are about equally bright. They both contribute observably to the spectrum. But the weird thing is that they must have very different masses. And you can see this just from the relative velocity amplitudes of the two stars. This one moves about 10 times more in velocity than this one, which implies a mass ratio of order 10. Also, the second star, the BE star, has only these rotationally broadened lines. Not surprising for a BE star, but that explains why when you look at the spectra, you don't see its absorption lines very obviously. And the final thing to note is that this narrow line star has relatively low surface gravity, 2.75. So that means, if it were a normal star, it would be a supergiant, or in the scenario I'll propose, it's a star that's currently in a sort of puffed up loaded phase. So now I'll show an evolutionary model that I and also others have proposed to explain the current state of these systems. So what I'll show here is effective temperature on the x-axis, surface gravity on the y-axis, and I'm going to show a binary evolution model calculated with MESA, which is a code that solves the stellar structure equations for two stars simultaneously. But I'm only going to show in this plane the evolution of the primary star. Okay, so you start out with a detached binary system. This model has a masses of 4 and 3 solar masses. And the primary starts on the main sequence, lives most of its main sequence lifetime like a normal main sequence star, not doing much. But at the end of its life, it starts to expand. And at that point, it starts to feel the tidal field of its companion. Gets a little bit distorted. And eventually, it starts dumping mass onto the companion through stable mass transfer. And so if you could observe the system at this point where the primary star is evolving up the giant branch while stably transferring mass to the companion, it would look just like Algol, the system that we talked about at the beginning. But as the evolution continues, the primary gets bigger, lower mass, and the orbit expands as well. And eventually, it reaches the tip of the red giant branch where all you really have is a helium core with a pretty thin leftover envelope of hydrogen. Helium burning starts in the core, and then rapidly the primary contracts. And on a pretty short time scale, it contracts to being a much hotter, much smaller star. But in the process of doing that, it goes through this part of temperature surface gravity space where we find HR 6819 and LB1. And it does that on its way to becoming a helium star. These are often also called SDOB stars. And in fact, in the last few years, there have been more than a dozen of these kind of BE plus hot subdwarf stars discovered, mostly in the UV using data from HST and other UV missions. When they get to this phase, it's very hard to detect the star that was initially the primary in the optical because it's so small, but it's hot. So in the UV, it's often detectable. And so our hypothesis is that these systems shed some light on how these ones formed. So in order to figure out, how common this kind of evolution is, we'd like to know something about lifetimes. So what I'm showing here is for the MESA model, the surface gravity of the star as a function of time since the tip of the red giant branch. And so we can define the current bloated phase as something like how long does it take for the star to get from the tip of the red giant branch to a surface gravity of 4, say, which is the surface gravity of main sequence star. It'll keep contracting after that. You can see that time is a few times 10 to the 5 years. So short compared to most stellar evolution timescales. Here's a plot showing the luminosity of the primary during that time. What's shown is the total luminosity in black, the hydrogen burning luminosity, the helium burning luminosity, and then the gravitational contraction luminosity. You can see during the phase we observe it now, it's really still dominated by burning the last residual hydrogen in the shell. But basically, as soon as a contraction starts, core helium burning begins in the core. And once you run out of hydrogen, that will be all that's left. So it's destined to become a core helium burning star. And you can also see that if you look at the mass, you can see the total mass is like 0.5 or 0.6 solar masses. But what's happening is the envelope mass is getting smaller as you burn through the last bit of hydrogen, and the helium core mass is getting bigger. And then if you want to know what happens next, you can zoom out. Here I was showing like 5 million years. Sorry, 5 times 10 to the 5 years. If I zoom out to show 3 million years instead, you can see that in a few million years, the star will contract to have a surface gravity of close to 6. So there's this core helium burning star, a luminosity that's a factor of 10 lower, and is dominated eventually completely by core helium burning once you run out of hydrogen to burn. In this scenario, the leftover hydrogen mass you get once the core helium burning star is very small, maybe 1% of a solar mass. So in this phase, these objects are studied pretty well. If they're not next to a BE star, you see them in a clump on the color magnitude diagram, or these are all these helium burning stars that have masses of about half a solar mass. As the mass increases, they go to higher luminosities, but it turns out that most of the ones you observe have masses of about half a solar mass, and they're easy to see when they're either isolated or more commonly when they have white dwarf companions because they're all in this clump. But if you put them next to a BE star, right, the BE star is also hot and has a much larger radius. So in the optical color magnitude diagram, they just look like BE stars. You don't see the companion. But if you go to the UV, then at least in cases where the core helium burning star is bright, you have a chance of detecting them. Okay, so we have one object or a couple objects in this phase, and we'd like to know something about the population. And so we've tried a few different ways to constrain how common these objects are. The first was just based on this object HR 6819, which is a bright naked eye star. It's magnitude like 5.5. And so it's hard to do any inference based on one object, but we did our best. And our argument went something like this. We have one object in this class that's a naked eye star. Most naked eye stars have been studied spectroscopically in some detail. So it seems reasonable to believe that this is the only one that's in this phase, or at least that there are not many naked eye stars that are in this bloated stripped phase. On the other hand, there are about 250 BE stars that are naked eye stars. So something like 1 out of every 250 BE stars have a bloated strip companion currently. On the other hand, the lifetime of this current bloated strip phase is much shorter than the lifetime of BE star, right? It's a few times 10 to the 5 years, whereas the lifetime of the BE star is just how long does it take until the BE star leaves the main sequence, which for the mass of the BE star in these systems is a few times 10 to the 7 years. And so the ratio of these lifetimes, about 250, is the same as the fraction of BE stars that currently have a bloated companion. And so if there were no Poisson uncertainties, from this I would just infer 100% of BE stars must have gone through this phase. But of course, the Poisson uncertainties are pretty large with n equals 1. And so just from Poisson uncertainties, the actual fraction of BE stars we think should have gone through this phase is somewhere between 20 and 100%. So big range, but it suggests that this is at least a significant channel for making BE stars. But I will say, so far this is obviously a hand-wavy argument because both of these lifetimes will depend on the particular BE stars, on the particular stripped stars, and because we didn't start with a well-defined parent sample to look in. Nevertheless, we can ask, what will happen, or rather, what does this imply about the BE star population? So if this argument is right, we expect that many BE stars should have these small, compact core helium burning companions, which in some cases will be detectable, but not in all cases. And so what's plotted here is for different mass core helium burning stars, you can see 0.45, 0.8, or 1.1, and a BE star like the BE stars in HR6819 and LB1, how much of the light as a function of wavelength is contributed by the core helium burning star once it contracts. You can see in the optical, these core helium burning stars, once they contract, are always very hard to detect. But in the UV, you have a chance of detecting them, especially in the far UV, and especially if you have an unusually massive core helium burning star, right? More massive than typical core helium burning stars at half a solar mass, then you can detect them. And indeed, there's been a lot of great work, going back a couple decades, but especially just in the last few years by Wang et al. To follow up with HST, BE stars that look like they might have these SDOB companions based on archival spectra, and I think there's more to be done there. But one takeaway from that work is these companions do exist, and the ones that are being detected are more massive than typical core helium burning stars seen in other places, which suggests that we might just be seeing the tail that we can detect and missing the part of the population that's lower mass and cooler. So this calculation was a start, but like I mentioned, one of the weaknesses was we didn't have a well-defined parent sample. We don't really know what the denominator is in calculating a rate, so we just said all naked eye stars. So to be a little more precise, we went to the APOGEE survey. So APOGEE is a near-infrared survey that actually mostly is looking at cool giants in the Milky Way, the steady galactic structure. But fortuitously, APOGEE also observes some hot stars. They're used mostly for telluric calibration for skylines. So APOGEE observes something like 5,000 B stars. Each one was observed at least 3 times. So you have at least 3 epochs, which means it's a good place to look for binaries. And so of those, there are about 300 BE stars. So we just looked at the multi-epoch spectra of these 300 BE stars and looked for ones that look like they have evidence of binarity. And I'll say first, we were hoping to find systems like HR6819 and LB1 in the APOGEE spectra, but it turns out APOGEE is not the right survey for doing that because in the near infrared, the bloated stripped stars in those 2 systems wouldn't be detectable. They don't have any narrow lines in the infrared. And so it turns out that what APOGEE is really sensitive to is the progenitors of those systems before they get so hot when they're a little cooler. And I'll talk about what I mean in a moment. So of the 300 BE stars we looked at, we found exactly 1. So one object we're looking for. So we're again in the Poisson n equals 1 limit, but at least we have a better parent sample. Here I'm just showing the APOGEE data for that star, and you can see there are narrow lines that shift back and forth in RV. And then here's a hydrogen line. This is the bracket series, which is the hydrogen lines you can see in the near infrared. And there's this double peaked emission inside the hydrogen line. So we did a lot of follow-up on this object since it was the only one we found. So we have a flux calibrated spectrum at low resolution, a high resolution spectrum, RVs, light curves. And when we model, I'm not going to go into the details, but you can ask if you want. When we model this, we can measure the temperatures, masses, and radii of both stars. And then we'll take those and I'll put the parameters of the mass of the bloated star onto the same plot that I was showing before, the temperature versus surface gravity. Now I'm also showing luminosity and radius. And what we find is that the system is well described by the same kind of evolutionary tracks that make HR 6819 and LB1, and also this other system I haven't talked about, which is in a similar evolutionary state, but it's at an earlier phase in its evolution, where there's still mass transfer ongoing. And so in that sense, this object HD 15124 is not yet a classical BE star, right? It does have emission from a disk, but almost certainly the disk is an accretion disk, not a decretion disk. Nevertheless, the B star with this accretion disk is already rotating much faster than normal B stars. It's about 60% of critical rotation, and it's probably still being spun up by ongoing accretion. And so these evolutionary models suggest that if we just come back in a million years, mass transfer will end, and the BE star will start on this track, and the system will have a similar evolutionary history to these other ones. Because mass transfer is still ongoing, the relevant time scale to use in our rate calculation is a little different. It's about 1 million years instead of a few times 10 to the 5 years. One really neat thing about this system is with the high resolution spectra, we can measure the surface abundances of both stars. And when we do that, we find strong imprints of CNO processing. That is, there's more nitrogen on the surface of the stars than you would expect, and less carbon and oxygen. In fact, the nitrogen to carbon ratio is more than 1,000 times that in a normal solar-like spectrum. And that's exactly what's expected in this mass transfer scenario. So what I'm plotting here is the expected carbon and nitrogen fractions. Oh, and it's also enriched in helium as a function of orbital period for the MESA model we showed. What's happening here is that the material currently on the surface of the stars is what was previously inside the convective core of the mass losing star when it was on the main sequence. And so that gets processed by CNO burning. Then you strip off the envelope and it's now at the surface. So you're essentially peeling an onion and looking inside the layers of the star that you can't see otherwise. So with this one object, we can do the same kind of calculation that we did with HR 6819. Again, we have a denominator of about 300 BE stars, but the lifetime of the phase where it would actually be detectable for our search is longer. It's about 1 million years. And again, the lifetime after the phase ends is about 50 million years. And so now this F stripped here, this is what fraction of BE stars have gone through a phase like this star is currently in, where they had a floated stripped companion. We can infer that. Again, we have a large uncertainty because n equals 1, but the median value is about 30%, and the 1 sigma range is something like 10 to 60%. So again, we find evidence that this is a significant channel for making BE stars. The upper limit suggests it's not the only channel. It's possible that some of them form through other binary related channels that wouldn't be in a phase like this, say stellar mergers, or maybe some of them form through other processes. I will say I tend to think of this number more useful as a lower limit than an upper limit. And the reason is that we only detect these systems where the BE star already has detectable emission lines from a disk. But it's possible that some progenitors don't yet have detectable disks. Okay, so that was the BE star part of the talk. In the last part, I want to go back to the search for stellar mass black holes, which is how I got interested in this problem in the first place, and which has had a lot of developments in the last couple of years. So just to motivate that, I'll say, the Milky Way contains something like 25 dynamically confirmed stellar mass black holes. And those are all in accreting X-ray binaries. So these are systems where you have a black hole that's right next to a luminous star of some type. And there's stable Roche-Loeb overflow transfer onto the black hole. The material around the black hole gets extremely hot, millions of Kelvin. And so when these systems are active, you can see them in X-rays all across the galaxy. We've learned a ton about black holes and about accretion in general by studying these systems. But it's worth just pointing out that these are probably not representative of the broader black hole population, right? They're just a very small subset of the black hole population. Their evolution is affected by having a close companion. The masses and spins of these black holes are very different from the masses and spins of black holes being discovered by gravitational wave searches, for example. So this motivated us to look for systems like this that are just more widely separated. And if they're more widely separated, there won't be mass transfer. The black hole won't be bright, and they'll be harder to find. But the way to search for them is basically to look for normal stars that are orbiting something massive and that you can't see. And we don't really know how common these kind of systems are, but we can take population predictions from models. Here's a model by Katie Breivik from 2017. And what's plotted here is the orbital period in days, which also scales with separation, of black holes that are predicted to exist in binaries with luminous stars. And then the y-axis is the mass of the luminous star. And if I just plot on top of this the known black holes in X-ray binaries, you can see that these all hug this inner envelope of the predicted population. And that's not surprising, right? These systems are as close as they could possibly be without just merging and without being on top of each other. But what's interesting for me, right, is that there's this whole population out here at longer periods and wider separations that's at least expected to exist. And so, if we could start to detect these systems, we could learn a lot about the black hole population. And there are many ways to look for them. I'll talk about a method I've been using, which is to look at light curves. And there are a few different ways you could hope to detect these systems with light curve variability. So one is to look for ellipsoidal variability. And that is if you have a normal star that's orbiting a black hole at a separation that's still pretty close, such as the tidal field is significant, but wider than in X-ray binaries, then the normal star will get tidally distorted. So it's not a sphere anymore, but it's kind of this teardrop shape. And then the cross-section of the star that you see changes as it goes around its orbit. So you see more of the star, and it's brighter when you're looking at it edge on than half an orbit or a quarter orbit later when you're looking at it end on. And so this leads to almost sinusoidal variability on the orbital period. And then there's another effect you can hope to look for. That's called Doppler beaming. And that is anytime a star is moving towards you, because of Doppler beaming, it's brighter than when it's moving away. The amplitude of that effect, though, is proportional to V over C, so it's pretty small. And the orbital period, the period of this is the orbital period, rather than half of the orbital period for ellipsoidal variation. So either one of these effects by itself would be hard to do anything with, because unfortunately there are all kinds of things that make stars vary in basically sinusoidal ways, and black holes are not the most common of them. But fortunately, when you put these two effects together, you predict a fairly specific light curve shape, which looks like this. We have adjacent peaks of different amplitudes. And if you know the mass and radius of your luminous star, then the relative amplitudes tell you something about the mass and inclination of the companion. If you're really lucky, there's one more effect you can hope to find, and that's gravitational microlensing, which is that when a compact object moves across the face of a luminous star, if you're viewing it edge on, that will focus the light of a luminous star into your line of sight, and the system will briefly get brighter. So it looks like the opposite of an eclipse. So this is all well and good. It suggests a way to look for black hole companions is look at a lot of light curves and look for systems that have this kind of shape. The reason this is hard is that unless the unless the binary is almost Roche-Loeb filling, the predicted amplitude of these effects is small, typically 1% for periods of order a week. So you need precise light curves. It is not like the case of algol from the beginning where you have a 100% variation. But fortunately, there's a satellite in space that's producing these precise light curves for many stars. It's called TESS. It's mostly looking for planets, but it's been used for lots of other areas of stellar physics, including studying BE stars. And there are about 20 million stars that are bright enough where we can get these sub-percent level light curves. Here's just an example of what this kind of data looks like. So here I'm showing a little cutout, a few arc minutes wide of a region that contains a few stars. And I'll just play time forward. So TESS takes one image every 30 minutes. You can see this star is obviously getting brighter and fainter, with about the right amplitude. And if I extract that light curve and just plot brightness as a function of time, you see I get basically the model I was looking for, where I have quasi-sinusoidal variability with adjacent peaks of different heights. So of these 20 million stars that are bright enough to get this kind of data on, I've extracted all their light curves, looked for things that have this shape, and from that, we found about 10 to the 4 candidates. Okay, about 10 to the 4 binaries whose light curves look like they're a combination of ellipsoidal variability and Doppler beaming from a massive companion. That sounds good, but of course, black holes are very rare, and just our a priori expectation is that a vast majority of these are going to be contaminants, right? Even though this is a specific light curve shape, there are still other ways to make light curves of almost any shape. So to figure out which, if any of them are promising, you need to get more data. And so for the last couple of years, we've been running this follow-up program using 2 telescopes, one in the north, one in the south. And basically what we do is for every candidate that looks good from the light curves, we get 3 epochs of spectra on different nights and just look for radial velocity changes. And then if we see the large radial velocity changes we expect, then we get a full orbital solution that looks something like this. And then from this orbit, if you know something about the mass of the luminous star, you get a constraint on the mass of the companion that you don't see. And then if that mass is bigger than some threshold, say bigger than the Chandrasekhar mass or bigger than the mass of the luminous star, then you're happy. So we've been doing this for a couple of years now, and we found basically 2 outcomes. The first is we get 3 RVs, and just from our light curve, we can predict what the RV should be up to a constant offset, because the Doppler beaming term is just proportional to radial velocity. So in the first case, everything works beautifully. The radial velocities are exactly what we expect from the light curve, and they're getting the radial velocities essentially adds no extra information because we already had them from the beaming term. Unfortunately, the second case is more common, is total catastrophe, where the light curve predicts you should have huge radial velocity variations, but in fact, you don't see anything from one night to the next. And in these cases, probably these aren't binaries at all, but instead we're seeing the light curve variability because of pulsations or because of spots on the stellar surface. So we've now gotten this kind of data for several hundred candidates selected by light curves. And we found a lot of binaries. So our success rate in getting things that are actually binaries is something like 40%. It's gotten better over time. But of those, we've tried to be conservative in what we claim is a black hole. And it seems like 0 of our few hundred have a black hole as the only plausible explanation for the data. We have, however, found a bunch of new kinds of binaries that we weren't expecting. And the class that's been the most interesting for me is these binaries that have 2 white dwarfs, or rather 1 white dwarf and 1 very low mass bloated proto-white dwarf. So this object is actually pretty similar to the hot subdwarfs that were found in HR 6819 and LB1 and those other systems, but just even lower masses, such that they're too low mass to ever start burning helium in their cores. we detect them in a phase where they're bloated. So although they're very low mass, they have radii comparable to the sun. And the reason these are contaminants for black hole searches is if you just interpret their colors as telling you about their masses, you would infer that their masses are about a solar mass. And then the radial velocities would tell you the companion must be at least 3 solar masses. And you'd say, well, I don't see that, must be a black hole. But the reason the argument fails is that actually their masses are not what you would expect just from their spectral energy distributions, because they're in a short-lived phase on their transitioning from being normal main sequence stars that have been stripped to being compact low mass white dwarfs. And so their masses are much lower than you would expect. So if I had to summarize my work on looking for black holes in one sentence, it would just be that the haystack is much bigger than you think, right? We expect that the number, that something like 1 in every million stars that we look at has a black hole around it, with give or take a factor of 10. And so anything that can go wrong will go wrong. And there are all kinds of contaminants that are astrophysically interesting and that you learn about, but that are not black holes that can produce the same kind of signatures that you look for in black hole candidates. And so just to emphasize that, in the meantime, while we've been doing this, there have been more black holes proposed in systems that have a lot of similarities with the ones I talked about before. Here are a couple from the last year or so. There are a couple more. Many of them come with these press releases with fancy pictures, but they don't last very long. So of the ones that have been published, I've written papers with, I think, alternative, better explanations for the data, as have others in the field. And I don't want to emphasize, I don't want to suggest that the people doing these discoveries have done anything wrong. It's just a very hard problem. It's much easier to find one thing that's wrong with the candidate than to prove that all possible things that could be wrong are not wrong. But we found a lot of cool interacting binaries in the process. Just for a little cheeky summary of the state of the field today. So here's a list of all the proposed black hole candidates that have from the last several years, but most of these are really the last 2 years since I started working on this. A black skull here means that, in my opinion, there's no way there's a black hole there. It's some other kind of interacting binary. And a yellow shrug means there could be a black hole, but I think other astrophysical explanations are more likely. There's one system where I haven't been able to find another explanation, although it doesn't mean it doesn't exist. But this one is in a globular cluster. So it's probably a different, it's very interesting, but it's probably a different kind of formation history than the black holes we find from stellar binaries that start with 2 stars. The one system that is dormant and which I'm confident about is Sagittarius A star. But I will say, we've been waiting several years for an EHT image of this one that hasn't come out yet, so we may still be surprised. Anyway, the haystack is bigger than we think, and we have to keep looking. So just as I end, I want to give a summary of data coming that will make this problem better in the next decade or so. So what's plotted here is spectroscopic surveys that get radial velocities for stars as a function of time. You can see very roughly the number of stars that have good spectra. There's no reason to think that will continue forever. A survey that I'm really excited about and have been involved some is SDSS-5. And the reason is not just that it's getting a lot of spectra, there are other surveys that get a lot of spectra, but that SDSS-5 is really targeting high mass stars, right? There's a program to get multi-epoch velocities for something like 500,000 OB and A stars, where the lower mass limit is something like 3 solar masses, but up to tens of solar masses. And probably those are the binaries that are most likely to have black hole companions, or certainly more likely to do something interesting in a binary evolution point of view. We also have light curves, where we've recently seen a huge increase from TESS, and TESS is as good as it will be for the next few years. But although we've already started to analyze these data and look for this kind of variability I talked to, there's still quite a bit of work to be done to process the data better and do better detrending and filter out false positives more efficiently. And the last thing I'm really excited for is at wider separations, we'll have binaries with astrometric solutions. And there's really only been one mission that has produced this kind of data before. It was Hipparcos. And it only produced astrometric solutions for like 200 binaries. But in just 6 months with Gaia DR3, we'll get the first tip of the iceberg for these astrometric solutions. Eventually, it's something like 60 million stars will have good enough astrometry that if they had a massive companion in an orbit of a few months to a few years, Gaia would be able to detect it. And so the kind of data we'll get will look something like this. I will say DR3 just being the first data release that has this kind of data will be a smaller subset where the Gaia team is sort of confident in the astrometry. But we are here. We can expect the amount of candidates produced by all ways of looking to continue to increase. The number of false positives will also continue to increase, but I think the community by now has started to appreciate that, much like a couple of decades ago when you're looking for planets, and there were a lot of planet candidate false positives, that there are many things besides black holes that can masquerade as them. But in any case, both for looking for black holes and for just looking for general interesting binaries is a good place to be. So I'll just leave up my summary slide. Basically says, binary evolution does a lot of interesting things. And looking for stellar mass black holes continues to be promising, but it's a hard problem. And you may accidentally learn more about binary evolution than you hope to in doing so. All right, thanks.
Thank you very much, Kareem. That was a lovely talk, really. It was really a joy to hear you speaking. And I actually understood like almost 100%, which is fantastic. So thank you very much. So does anyone have a question for Kareem? You can either just turn on your mic or raise your hand. I don't see any hands up just yet. If no one has a question, I have a question. It's mostly about what you're planning to do from now on, because you still have like 10,000 candidates for these black hole systems. Are you still going to be sifting through them to try to find your needle?
Part of the problem is for every 20 candidates, it means it's one night that I can't sleep because I'm at the telescope. So what we're going to try to do for most of them is through SDSS-5, there's this open fiber program where the community can submit just interesting stars that they'll put a fiber on and get a spectrum in cases where there's a spare fiber. So we submitted our 10,000 through that, and the hope is that over the next 5 years or so, all of them will get 3 bucks. So we're mostly switching to that mode rather than observing each one by one. We've also gotten better at eliminating false positives just based on analyzing the light curves in different ways. And for every false positive we find, we have a new set of objects to try to eliminate that are the same kind.
Oh, right. Oh, okay. So lots of hands up now. I think Doug Guys was the first one.
Hi, Kareem. This is Doug Guys. Thank you for your wonderful talk and actually really amazing work. I had one quick comment and then a question. The comment was Robert Clement, a colleague who's working at the Char Array, has recently used the interferometry to detect subdwarfs in 3 cases, and there's a paper out on arXiv now. So with interferometry, you can actually get down to luminosity ratio, flux ratios of about 300 to 1, something like that. So it really is possible to start picking out some of the fainter companions that way.
That's awesome. I do remember seeing that paper. I just forgot to mention it.
Yeah. And then the other question I had for you was on your search for black holes with the light curve. I would imagine with TESS, you're sort of limited to relatively short orbital periods because of the cadence with TESS. Have you thought, or has anyone looked at the Kepler data where you've got a much longer time span?
Yeah, that's right. So with tests, we're only sensitive to periods less than a couple weeks. I have run the same search on Kepler, and a few of the candidates we followed up were from Kepler also. It's just a much smaller part of the sky and fewer light curves. So none of the ones we followed up had massive enough companions. I will say Kepler found some of these self-lensing systems where the companions are white dwarfs rather than black holes, which is basically the first step in any search for black holes is you should find a lot of white dwarfs first because they're much more numerous and have the similar effects. The other thing that's better with tests is just that by now people have figured out how to detrend the test light curves really well, whereas with tests often our detrending is still not perfect, and so if our model is not a great fit, we don't know a priori whether it's not a great fit because actually it's a spotted star and the spots are evolving, or just because there's some residual on detrending that wasn't perfect.
Okay, I think the next question goes to Dietrich.
Yeah, very nice talk, very clear, very convincing. And I should say that I fully agree with your version of the HR 6819 story. So congratulations on that, very well done.
Thanks.
My question concerns similar BE plus SD binaries, where it seems that all the BE stars that have been discovered to have such a companion are early type BE stars, or most of them. What sense do you make of that?
Yeah, that's a good question. I mean, I will say, I think both of these systems, the BE star is like B3, so it's not. I mean, I think it's less early than the frequency where BE stars peak. I think. I mean, I think it's basically a flux ratio argument where the earlier type BE stars started with more massive binaries. The primary in the binary had to be more massive than the BE star initially. So if it was more massive, it produces a hotter helium core, which is easier to detect. But also there's more contamination from there's more dilution from the BE star. So I haven't done the sort of population synthesis calculation you'd have to do to decide whether that's a surprise or not. I will say just naively, it's not what I would have expected either. I would have thought later types, the BE star is less bright in the optical, so you have a better chance of detecting the companion.
Thank you.
And next it's Daniel.
Yeah, hi. I agree. It's super nice talk. But I have a few questions about this AB1-like systems. Yeah. What is the hydrogen surface abundance of these B-type stars? Because you always talk about the strip star, but how much is really stripped from the star? So.
Yeah, good question. It's in the papers. I don't remember the exact numbers. I believe in this current phase right now, the helium abundance is something like 4 times larger than it should be for a normal solar type star. So it's YE is like 0.6, the mass fraction. In the MESA models, predict you basically go from normal hydrogen abundance up here to very low hydrogen abundance down here, but then again, they're settling later on, so it's more confusing. I think particular in HR 6819, there were 2 papers that did similar analysis, one by me and one by Julia Bodensteiner, and we got fairly different values for the helium abundance. So I found it was definitely helium enhanced, where she found close to normal helium abundance. And it really just came down to using different sets of spectral models. So I used these T-Lusty ones, and she used the Potsdam-Wolf-Rayet ones. And I don't yet have a good sense of whether that's an easily resolvable issue for the spectral lines or not. with the atmosphere models or not. Yeah.
Mhm.
I will say
Okay.
also in this HD 15124 system up here, their our helium measurement is I'm pretty confident in it, and it's also like 3 or 4 times higher than primordial.
But it was still higher than in the predictions of the model, right? In the plot you showed. So the measured value was higher than the model prediction. Okay.
That's right.
And if I can ask another question about these models, yeah. So one only just sees this straight line, but what is the probability that the system is in this phase? So is it a long enough phase that we actually can observe it, or is it predicted to be a short-lived phase and we are just lucky to catch it there?
Yeah, so it's pretty short. So, you know, the main sequence evolution before anything happens, right, is like tens of millions of years or 100 million years. Then this trip up the giant branch is, you know, at most 10 million years. And then this contraction is very short. It's like 500,000 years. So you do, I mean, that's sort of why, even though we only found a couple systems, we argue that if our interpretation is right, there must be many more that have gone through it, because it is short-lived. It's not as short-lived as you might naively expect, because like initially people said there's no way you catch it here because contracting on a thermal time. And it's not the thermal time isn't what's relevant, because it's still powered by hydrogen shell burning. So it's how long does it take to burn through the rest of the hydrogen shell. So it's short, but it's, you know, if you look at enough stars, you expect to find some there.
And one last question about it. So you already showed this keel diagram, but where would they be located in the Hertzsprung-Russell diagram? So would these companion stars be hidden in the typical B population, or would they already be more to the left or on the right side of the Hertzsprung-Russell diagram?
Yeah, so it depends on where you catch them. What, you know, these systems here, their luminosities are very similar to normal B stars of the same temperature. And I mean, that's why people interpreted them as normal B stars. It's really only if you can measure surface gravity or come up with other reasons that they have to be bloated, that it's obvious. I think I somewhere I had I have a plot somewhere that includes luminosity. I think it's, let's see. Yeah, here's the luminosity track. So you can see the main sequence here is this dashed line. So these 3 systems look pretty much like slightly evolved B stars. This one, which is still mass transferring, is quite a bit different, because it actually gets fainter when mass transfer starts, and then only later again.
Okay, thank you very much.
Any more questions? It's really a shame we can just jump into the future a million years to see how the system is going to turn out.
Yeah, that often is.
Oh well. Okay, I think that's it for today. If no one has any more questions, I would like everyone to thank Kareem virtually, send him his applause, and thank you very much. And I see everyone next month for the next talk in our series.
Yes.
Thank you.
Thank you. Thanks, Amanda, for being the host today. And thank you, Kareem. That was a very interesting talk. Much appreciated.
Thanks for inviting me.
Have a great day, everyone.
Bye.
Bye.